Hello, I'm Mark Chen. I'm a fellow in CIFAR's Gravity in the Extreme Universe program. And tonight I'm going to tell you about how we're exploring the dark universe from 2 kilometers underground. So let me start with the composition of the universe on this first slide. So since the dawn of civilization, mankind has sought to understand what are the fundamental constituents of the world around us. What are the elements, fire, air, water, earth, from antiquity. The Greeks introduced the concept of the atom. Chemistry brings us the periodic table of the elements. Particle physicists develop a standard model of the elementary particles. And cosmology and astrophysicists have observed the properties of the galaxies and in the cosmos, as well as the cosmic microwave background, the imprint of the radiation from the Big Bang, looking at the universe's earliest baby pictures in order to understand that this is the composition of the universe, that the universe is made up of something called dark energy, which I won't be able to describe tonight, and that's the dominant composition component of the universe. There's something called dark matter, which I'll try to describe for you. And the ordinary matter, that the particles that we understand, that make up the stage, that make up the TELUS Spark Center, that make up you and I, that's only 5% of the universe. And so what is this dark matter? We have evidence for dark matter from this image, but also from many observations in astrophysics. This image is actually a composite of 3 different images. There are galaxies that are in the background, an image, and overlaid in red is an image in the X-ray showing hot gas that resulted when 2 galaxy clusters billions of years ago have passed through each other, and the resulting interaction of the gas gave rise to that signature that's observed. But what's also shown is the gravitational image in blue, and that gravitational image is produced by some matter, and we see that matter is what's responsible for clumping ordinary matter that make up the galaxies that are observed, and that this blue material, this matter, has actually passed through each other without interacting. So this is, that image tells us something about what dark matter is. What physicists have figured out in terms of dark matter is that we know that dark matter is non-baryonic. That means it's made up of particles that are not like ordinary matter, that are like the protons and neutrons and electrons that you might be familiar with. Physicists know that the dark matter is very weakly interacting because it appears to be collisionless, so that its interactions are purely gravitational as far as the observations that we can make. That dark matter is cold, it's made up of non-relativistic particles, that it clumps together because of gravity, and as a result, the dark matter provides the seed that allows galaxies, clusters of galaxies, the large-scale structure of the universe to exist as we observe it. And as our simulations can predict and be compared with observation. But what physicists don't know is exactly what kind of particles form the dark matter that pervades the universe. And there are several ideas, and the leading ideas include something called supersymmetry that produces a WIMP, a weakly interacting massive particle, extra space-time dimensions. The excitations could be a particle of, could manifest itself as a particle of dark matter, something called axions. And so the question is, how do we detect dark matter? How do we determine what it is? And on this slide, it's a simplified overview of the ideas that particle theorists have about dark matter. And it shows that there's many, many ideas. And I'll point out, actually, this slide comes from 2013. And that's 7 years ago. In the 7 years, we haven't simplified this any further. So still, our picture from theory is like this. But we need to go after this to understand the nature of dark matter with experiment and see what that tells us. So one of the types of experiments that is pursuing the detection of dark matter is to build very large detectors deep underground. So we seek shelter underground from cosmic radiation. So we're constantly bombarded by radiation from space, high energy particles that rain down on us. And so we go deep underground, and so that these particles will be screened by the material above. And so when we locate our very sensitive detectors below, we're hoping that these very weakly interacting particles will pass through and that we can observe them that way. And so in Canada, we have one of the world leading facilities for this type of physics experiment. And what we have is in the, one of the mines, one of the very deep mines in Sudbury, we have an underground lab that's called Snow Lab. And what we've done really over the past 20 years is we've carved out of rock and produced a very quiet location where we can place the most sensitive detectors to search for dark matter. And so Snow Lab is a follow-on to the Sudbury Neutrino Observatory. The results from that original project garnered the Nobel Prize for Art McDonald in 2015. And so we're continuing with Snow Lab with new experiments. And I'll just show you a few of the pictures of what we're doing. And then afterwards, if you're curious about what these detectors are, then please come and talk to me. So here is an illustration. Here are photos, no illustration, photos of the new neutrino detector as it's been refurbished. And you can see that here my colleague is putting the finishing touches on the upgraded neutrino detector that's currently taking data now. This is a detector that's filled with 3,000 kilograms of liquid argon. So liquid argon is at minus 190 degrees Celsius. It's argon is a gas that's abundant in ordinary air, and when you cool it down to those temperatures, when you liquefy it, it becomes a detector that then produces flashes of light that can be very distinctive between interactions of dark matter and ordinary matter. And here, this detector is cooled to below 1 degree above absolute zero. And when dark matter particles will strike this detector, it'll produce a pulse of heat up these detectors a small degree, and they can be measured with very sensitive detectors. And we're also hoping with this installation being installed in Snow Lab in the next few years that we'll try to detect dark matter that way. And so the quest to understand the nature and composition of the universe continues, and I think there's light at the end of the tunnel. Thanks very much.